Hello, good day. I'm Mr. Ernesto Otanes of the Physics Department, Mapua Institute of Technology. I'm here to discuss the theory of relativity, but we'll be concentrating mostly on the application or problem-solving part of the theory of relativity. The first part in the application of the theory of relativity is the measurement of the mass of the body, which is moving with the velocity approximately equal to the speed of light. And you call that mass relativistic mass. It is stated that a body in motion relative to an observer is measured to have a greater mass than when it is at rest relative to an observer. And the mass can be computed equal to the ratio between m sub o over the square root of 1 minus b squared over c squared, with m sub o as the rest mass, or it is the mass of the body when it is at rest relative to observer, while m stands for relativistic mass of the body, which is the mass of the body when it is in motion relative to the observer. Given are as follows. Mass of Poki, which is at rest with the observer when he is on the ground, is 70 kilograms. Then for the mass when he is in flight together with spacecraft, the mass is 100 kilograms. The requirement is to determine the velocity of spacecraft where Koki is a rider. So if we're going to apply the mass formula, that would be equal to m sub o over the square root of 1 minus b squared over c squared. Then substitute the values. M is equal to 100 kilograms. M sub o is 70 kilograms. Then divided by 1 minus b squared over c squared. And you can see in the formula the unknown velocity. And for you to determine this, of course, apply the mathematics part by separating this from the constant. So that would be square root of 1 minus b squared over c squared. That would be equal to 70 over 100. And the ratio is equal to 0.7. So to determine the velocity, we have to remove the radical sign. That means squaring both sides. The result will be 1 minus b squared over c squared equal to 0.7 squared. Then separate the ratio between b squared and c squared from other constant. So the result will be b squared over c squared equal to 1 minus 0.7, which is 0.49. Then separate b squared from c squared, transferring it to the other side. Then it becomes b squared equals to c squared multiplied by difference between the two, which is 0.51. And to determine the velocity, extract the square root of both sides. Then the result will be b equal to c square root of 0.51. And yun lang ang 0.71. Now, the answer can be expressed in terms of a multiplier for c. But if you want to know the exact value, then substitute the value of c, which is 3 times 10 to the 8 meters per second. Then multiply it by the multiplier of 0.71. The c get will be equal to 2.13 times 10 to the 8 meters per second. And that's how fast the spacecraft will be moving with respect to the observer on the ground. The next application is the relativistic length or length contraction. The object, when it is traveling with a speed approximately equal to the speed of light, the length of the object decreases when it is moving relative to an observer. And so for the relativistic length, L will be equal to L sub o times the square root of 1 minus b squared over c squared, where L sub o is the length of the object at rest with the observer, and L represents the length of the object when it is traveling at a speed relative to an observer. Now, for the application, as stated in problem, we consider an observer on Earth, on the ground. When the meter stick is on Earth and at rest with the observer will see this meter stick having a rest length which is equal to 100 centimeters or equivalent to 1 meter. Now, if this meter stick is now considered to be in flight, part of a spaceship, and this spaceship is traveling with the velocity equal to 0.8 of the speed of light, the meter stick is considered to be also moving with the velocity. Thus, this observer will see this meter stick having a length that is already contracted. So, if we're going to apply the length contraction formula to solve for the new length of the meter stick, L will be equal to L sub O multiplied by the square root of 1 minus B squared over C squared. So, substituting the value, solving for L, rest length will be equal to 100 centimeters multiplied by the square root of 1 minus, substituting the velocity now, it will be 0.8 of the speed of light raised to the second power over C squared. And then further simplifying the equation, L will be equal to 100 centimeters multiplied by square root of 1 minus. There's no need to multiply 0.8 by C, but instead square, square both factor, 0.8 squared multiplied by C squared and dividing it by C squared. You can see that it will be easy to simplify this ratio because C squared and C will cancel out. So what will be left will be 0.8 squared. So continuing the simplification of the equation, L will be equal to 100 centimeter multiplied by 1 minus square root of 0.8 is 0.64. Then get the difference. The difference will be equal to 0.36, and square root of 0.36 is equal to 0.6. Thus, the length would be 100 centimeters times 0.6, or the value that you get will be 60 centimeters. The next application is the relativistic time or time dilation. Now, it says that a clock moving with respect to an observer appears to tick less rapidly or slowly than an identical clock at rest relative to an observer. It is the lengthening of the time between events that occur on an object moving relative to an observer. So, if the clock moves relative to observer, traveling with the speed approximately equal to the speed of light, the time recorded by the clock appears greater than the time recorded by the observer when the clock is at rest with the observer. And to compute for the time dilation, T will be equal to T sub O over the square root of 1 minus B squared over C squared, with TO as the time recorded by the clock as seen by the observer when the clock is at rest with the observer, and T as the relativistic time when it is recorded by the clock, which is traveling with the velocity approximately equal to the speed of light with respect to the observer. For the application, the problem says that a space probe travels at 0.8 of the speed of light relative to Earth. 30 days on Earth correspond to how many days inside a space probe? To solve the problem for time dilation, as stated in the problem, there is an observer on the ground, on Earth, seeing the clock, recording the time, which is at rest with him. Since the clock recording time is at rest with the observer, the time recorded by this clock, as seen by the observer, is 30 days. Now the question is, how much time will be recorded by the same clock if the clock is now traveling with a speed approximately equal to speed of light and the value is 0.8 of c. So here's the clock which is part of that moving spacecraft. What will be the time recorded by the clock as seen by the observer from the ground? So from the time dilation formula, T will be equal to T sub O over the square root of 1 minus B squared over C squared. Then to substitute the value, T is equal to T sub O, which is 30 days over square root of 1 minus B squared over C squared. Then substitute the value of B. Instead of B squared only, it will be represented by 0.8 of speed of light. Then squaring that factor, 30 over square root of 1. Then factor out 0.8, it will be raised to the second power. C squared over C squared. C squared will cancel out, so what will be left will be 0.8 only. And then further simplifying the equation, T will be equal to the square root 30 over square root of 1 minus 0.64. And the difference between 1 at saka 0.64 is equal to 0.36. And we know na when you get the square root of 0.36, the result is 0.6. So this becomes 30 over 0.6. And the resulting time recorded will be 50 days. So that shows that the clock recording the time when in space traveling with speed approximately equal to the speed of light will record the time greater than the time recorded by the same clock as seen by observer on Earth.